Gibbs free energy and the equilibrium constant. For Gibbs free energy, we know that when a reaction is at equilibrium, delta G is 0. When it's spontaneous, delta G is less than 0. Non-spontaneous, delta G is greater than 0. We also know from earlier studies that at equilibrium, K is equal to 1. Spontaneous, K is greater than 1. Non-spontaneous, 0 is less than K, which is less than 1. Comparing these two sets of information, we find the relationship between delta G, Gibbs free energy, and K, the equilibrium constant. When delta G is 0, K is 1. Delta G less than 0, K is greater than 1. Delta G greater than 0, 0 is less than K, which is less than 1. To determine K for a reaction and how it varies with temperature, we can use what we learned about delta G. If delta H and delta S have opposite signs, the reaction is irreversible and will not have an equilibrium temperature. In that case, if delta H is less than 0, and therefore delta S is greater than 0, then delta G is less than 0 and K is greater than 1, and the reaction is spontaneous and product favored. If delta H is greater than 0, and therefore delta S is less than 0, then delta G is greater than 0, and 0 is less than K is less than 1. And the reaction is non-spontaneous and reactant favored. So again, you might want to pause this video and write this out a couple times to help you remember it. If delta H and delta S have the same signs, there will be an equilibrium temperature. At this temperature, delta G is equal to 0 and K equals 1, and the reaction is reversible. We use the same formula from the last topic to find T equilibrium. If your answer is negative, the signs of delta H and delta S must be different, and this formula shouldn't have been used. See the previous slide. K cannot have a negative value, and there is not a T equilibrium. If delta H and delta S are both positive, the value of delta G will become increasingly negative as the temperature rises above T equilibrium. As a result, K will increase above 1, and the reaction becomes spontaneous and irreversible as the temperature rises above the equilibrium temperature. The reaction will become increasingly product favored as the temperature rises above the equilibrium temperature. This does not require high temperature. It occurs at any temperature above T equilibrium. This could be a very low temperature as long as it is above T equilibrium. It depends on the reaction. Now, if delta H and delta S are both negative, the value of delta G will become increasingly negative as the temperature drops below the equilibrium temperature. As a result, the value of K will increase above 1 as the temperature drops below the equilibrium temperature. It will become increasingly product favored as the temperature drops below T equilibrium. This does not require a low temperature. It occurs at any temperature below the equilibrium temperature. It could be very high temperature as long as it's below the equilibrium temperature. It depends on the reaction. Using information previously learned in studying equilibrium, delta G can be adjusted to non-standard conditions using this equation. And let's see, delta G 0, right, that's the change Gibbs free energy under standard conditions, which is 1 atmosphere of pressure and 298 Kelvin. What else is in this equation? R, that's the universal gas constant, and here's its value. T is the temperature in Kelvin, and Q is the reaction quotient. So if we have a reaction where A and B react to form C and D, we calculate Q as follows. All right, here's the pressures of C and D, where C and D are our products, A and B are the reactants, and we're going to show this on the next slide. We'll show an example. Key point. Only reactants and products, which are gases, are included in the reaction quotient. Any substances that are not a gas are omitted. Let's examine the formation of nitrogen dioxide from nitrogen oxide plus oxygen. We have non-standard conditions. Why? Because right here are the partial pressures of the various gases. And remember, all we deal with are gases, but that's all we have in this equation. And here's our temperature. which of course is at a standard condition, but the pressures are not. So here's our Q value. Right, we take NO2, its partial pressure, and we square it because of this number right here, divided by the reactants. And we square the nitrogen oxide term, and oxygen is just linear. So we put in our numbers, we get a Q value, then we use this correction equation, substitute in our numbers, and we get delta G is minus 53.8 kilojoules. Since delta G is negative, the reaction is still spontaneous under these conditions, but less so than under standard conditions. And we'll explain that on the next slide. Under standard conditions, Q will equal 1, since all partial pressures sum to 1 atmosphere. As a result, delta G is equal to delta G at standard conditions. The term RT ln Q, ln's a natural logarithm, can be looked at as a correction factor for the non-standard conditions. A Q value less than 1 would make that term negative, which would cause the delta G to become more negative and therefore more spontaneous. This can be useful in determining what pressure conditions would be required to make a non-spontaneous reaction become spontaneous. We can then use this equation to develop the relationship between delta G and K. We can also use this equation to develop the relationship between delta G and K sub P, the equilibrium constant in terms of partial pressures. When a reaction is at equilibrium, delta G is 0 kilojoules and Q is equal to K sub P. Recall then this reaction. Kp is calculated as follows. It's the partial pressures of the products divided by the partial pressure of the reactants, and each partial pressure is raised to its coefficient. The partial pressures are in equilibrium at the given temperature. At another temperature they would change, which would change K sub P. At equilibrium, we have delta G equal to 0 and Q is equal to K. So we're going to take this equation here and modify it. So here it is again. We substitute in delta G is 0 and Q is equal to K. We then solve it for delta G 0. And then we want to solve it for K. So we isolate K on this side here. And then what we do is we E to ln K, and we do E over on the right side. That's legal. You can check with your math teacher. And we get K is equal to E to the minus G over RT. Now, be careful about units. Delta G is presented in kilojoules per mole, so we use this value for R. But the issue is delta G, if you have it in kilojoules per mole, like we're saying here, you have to convert that to joules per mole. Doing a little summary here, when delta G equals 0, the reaction is at equilibrium. When delta G is less than 0, the reaction is spontaneous. And when it's greater than 0, the reaction is non-spontaneous. We've learned how to calculate delta G at standard conditions using thermodynamic data. We can now discuss how to calculate delta G under non-standard conditions and how the values for delta G and K can be related. Let's look at this reaction where we have iodine plus chlorine, both in gaseous form, combining to form iodine monochloride. We're given delta G at standard temperature and pressure, and we want to estimate the equilibrium constant at 25 degrees Celsius for the above reaction when all pressures are at 1 atmosphere, which of course is standard conditions. Then calculate delta G when the reaction is done at 25 degrees Celsius, when the partial pressures of iodine and chlorine are 1.44 atmospheres, and the partial pressure of iodine monochloride is 0.150 atmospheres. Let's first find the value of K, and we're going to use this equation, and we solve that for K, and we get E to the minus G0 over RT. We then substitute in values, and be sure to keep the units consistent, since delta G is in kilojoules and R is in joules. So what did we have to do? We had to make sure this is in joules, right? Kilojoules, turn it into joules, and we get K is equal to 451. Note, the answer does not have units. Now we're going to find delta G when the reaction is not done at standard conditions. So we have our equation here. We have our delta G0 standard conditions, which we found on the previous slide. Then here's R, here's T, and here's the log of Q, which of course are the partial pressures. And then what do we have? Delta G is minus 20,700 joules, which is minus 20.7 kilojoules. So we had to go back to kilojoules because that's where the answers are typically reported in. Coupled reactions. A thermodynamically unfavorable reaction can be made favorable when it's coupled with a reaction that is thermodynamically favorable and shares an intermediate reaction. The sum of the individual reactions results in a negative value for delta G. Think about Hess's law, which we covered already in the course, making the thermodynamically unfavorable reaction spontaneous. One way to look at that is the energy from the first reaction drives the second reaction. A great example is found in biological systems. The conversion of ATP to ADP is thermodynamically favorable, having a large negative Gibbs free energy value. Whenever energy is needed in a cell, ATP is sent to that location to provide the energy, making a reactant-favored process a product-favored process. Let's illustrate that with an example. Consider the reaction for the decomposition of calcium carbonate into calcium oxide and carbon dioxide gas. The Gibbs free energy for this reaction is positive, making it thermodynamically unfavorable. However, that reaction can be coupled with the below reaction for the combustion of coal, which is a thermodynamically favorable reaction. Why? Because delta G is less than 0. And let's see, there's coal right there, carbon in its solid form. Now, if we add those two reactions together, coupling them, the overall process has a negative value for Gibbs free energy. So here's calcium carbonate all by itself, which has a positive delta G, and here's coal, negative delta G. We add them together. So right over here, that's going to be on the left side. So what we're doing is we're adding carbon to calcium carbonate and then oxygen. On the right side, our products are now calcium oxide plus 2 carbon dioxides. We add these two guys together. We now have a delta G of minus 264.0 kilojoules per mole, negative. So we now have a spontaneous set of coupled reactions. So remember, when we used Hess's law, if we add reactions, we add the delta H values to get the total enthalpy of the reaction. The same thing works for delta G. They can also be added to get the total Gibbs free energy, delta G, for the reaction.